All right, hello everyone. Welcome to the third meeting for the PCB design. Thank you all for showing up. This one, we're going to go over a lot more kind of conceptual stuff before we jump into the tracing. Just some stuff that you need to know before you actually start putting your tracks in Altium. So again, my name is Adam. I'm Darian. And we're just going to kick this off here. I'm gonna close the door too. Cool. So today we're going to kind of briefly go over schematics again, package sizes, tracks and vias, polygons, clearances, placements, and basics of EMI routing. So you guys are all kind of familiar of doing your schematic before. I just wanted to give you a couple tips and stuff for future schematics and things like that. First of all, the kind of idea of like garbage in, garbage out. Whatever you put on your schematic, if it's not properly organized and easy to follow, when you do your PCB, it could just be a lot harder to follow those same traces, tracks, and everything else like that. So there's a couple key things that you want to do when you're building your schematic. What's big in any sort of PCB that has multiple parts is sectioning off those parts in blocks and kind of labeling them. For example, right here is our power regulators. So everything that kind of has to do with the power, including like a battery connector or any sort of 5-volt regulator, a 3.3-volt regulator, I kind of sectioned those schematics off to the side a little bit, put a box around it and labeled it power regulators. That way I can kind of see where the different blocks are in my schematic and be able to kind of easily find things or make it a little bit easier to read. Next thing are kind of the net labels. And we went over that last time where you can net label each one of those little traces that you're drawing there, the little wires. That way, when you do actually get to your PCB, it's easy to read. For example, if you scroll into a trace, it says, 3.3 volts or ground or signal line or MPU 6050 interrupt. Just labeling each one of these little individual tracks with net labels makes it a lot cleaner in terms of just visually seen, so you can scroll and see where things are. But they also allow you to know what wires are what once you do start tracing. Another thing, when you are putting your components into your schematic, make sure that you're giving them the labels of, for example, if it's a 220 ohm resistor, below the designator, for example, R1, R2, R3, they're going to have a little name there. And in that name, you can put the value of your component. So if it's a resistor, like a 220 ohm one, you can label that in there so you kind of know by just visually seeing what value it is. And then this is just a kind of a blown up picture of it. This specific one is for our micromouse project that we have running. This is just kind of the microcontroller you're using, our serial interface to actually program our microcontroller, and our power regulator. So I just kind of sectioned them off there. Here's an example of kind of a more well-established company doing a schematic. They have a little bit different way to do it, but it's the same idea of sectioning things off into blocks. It's kind of hard to read here, but this is I squared C pull up and shift. So they labeled that off there, or this is the power supply. So they just kind of put different blocks of components in different locations. And then this would be the actual chip and things like that. So just for readability, it's really key if you have any sort of a multiple part schematic or PCB going in your schematic, make sure you do blocks and stuff so it's a little bit easier to read. So package sizes. Again, we kind of went over package sizes a little bit last time. So again, for your passive components like resistors, capacitors, inductors, or ferrite beads, you have the PCB ruler to kind of generally see those sizes. So remember last time we chose 0603. However, all those kind of passive components have the same footprint. So you want to choose one that has that specific size, Yeah, another important thing is if you do have your PCB ruler up, you'll notice that next to it, so for example, the 0603 one here, you'll see it says 0603, but in parentheses on it, it says 1608M. So that would be the imperial size of it. So it's the same exact thing. It just means one is the metric on the left, imperials on the left and metrics on the right. So you want to make sure that you're choosing the correct one. In the past, we've had a board that kind of gotten mixed up because if you realize there's two 0603s, there's 0603 imperial, which is a little bit bigger, and 0603 metric, which is the smallest one on there. And I don't know where it is right now, but we have the board in here where you can't even see the resistor. It's like literally a grain of sand on there. And that's because when we were doing the PCB, we mixed up the imperial versus the metric sizing for that passive component.
Right?
Yeah.
You can see it later.
Yeah, we can show it around later, but it's kind of crazy. Next, that's for kind of your passive sizes for smaller things like this. So this would be like a ceramic capacitor. This would be an electrolytic, which kind of has its own sizes, which are kind of a little bit bigger like that. And these two would be tantalum capacitors, which is another type of polarized capacitor, one that has a positive side and a negative side. So other than your passive components, you also have your ICs or your integrated circuit chips. These ones, there's some labels that are pretty generic. For example, your DIP package or dual inline package is what you'll put on your breadboards and see in your 201 classes or any type of chip that fits on a breadboard where it has those exposed leads like that. That's pretty common. However, things like SOP, they might have like 3 or 4 different names. It's kind of a mess if you're trying to understand it, but just know that we have a couple different footprints that, like, for example, this one is a ball grid array. So underneath the chip, there's a bunch of tiny little balls right there that are our pins. So it's completely hidden underneath the chip. It's really small, and you can have a lot of pins with that. But at the same time, you know, it's impossible to hand solder. So you would need something like a hot plate or a hot iron or a hot gun and solder paste to be able to solder something like that. And in addition to that, things like QFN package, which actually I believe the MPU 6050 is the QFN package right here. And you can see there's no exposed leads going on the outside. So our connections are just kind of little like pads underneath the chip like that. That is another one where it would probably be impossible to hand solder something like that. But it's a little bit easier than something like a ball grid array. Then we have, I believe it's a quad flat package, which you'll see a lot of microcontrollers are, where it's just kind of a big square with a bunch of pins off to the side that are actually exposed. And then SOP or small outline packages kind of look like that, or a bigger one right there. And then lastly are just like some transistor packages. And all these are surface mount components. And the reason I'm kind of recommending surface mount components rather than through hole is because in industry, it's pretty unlikely that you'll ever have a through hole component unless it's necessary to be through. When you can make something, you know, 1/8 of the size on a surface mount, man, it's 8 times bigger for a through hole. It doesn't really make sense to have through hole components. So in industry and honestly in our project clubs, I would really recommend surface mount components. So the next thing I'm going to go over are tracks and vias. These are our actual wires on our PCB. And there's kind of 2 things that we need to look at when we're choosing our track and via size. First of all, so it's essentially just a little piece of copper, no different than like a wire, for example, except it's placed on top of the board. And you can see on these ones, it's all exposed like that. Then you have your width and your thickness of that trace. Oftentimes, you won't really have to worry about the thickness. 99% of the projects that you'll probably be using is going to be on like 1 OZ, which is the standard thickness of that. However, if you're going to be doing something like something that has a lot of power or for whatever reason you need more thickness, you can change that. The main one that we're going to be focusing is track width. So that is like how wide that track is. And on the PCB ruler, we can see kind of a metric right here of what our typical track widths might be. And so you can see that it starts off really small at 0.2 millimeters and then goes all the way up to 2.5 millimeters. And again, you want to choose a trace width that can take the current that you need. For example, 0.25 can actually take up to an amp of current. 99% of the time, you won't need to increase that for things like signals or just interrupts or things like that. But if you're going to have any sort of power going to things, it's recommended to have a little bit of a thicker trace just for impedance and allowing a little bit more current. So this is a quick rubric. So you can see here the current that it can fit through that specific trace, or what's recommended to go through those traces. The width for 1 OZ, which is that thickness, or 2, which is a little bit thicker of a trace. So for example, 1 amp can go through a 10 width trace. So you can see on the ruler, 10 width or 10 millimeters or 10 mil, I guess. Yeah, this is a mils. 10 is going to be that 0.25 millimeters or 10 mil. So that trace right there that you see on that ruler can take up to 1 amp. Usually recommended to go bigger if you're going to be expecting 1 amp going through such a tiny trace like that. But just know that there's general rubrics you can look up to figure out how much current a specific trace can take. So the next thing I'm going to go over are vias. Vias are tracks that connect one side of your board to another. So on your PCB ruler as well, you can kind of see you have vias kind of on that left-hand side, the bunch of small ones right there. So they look like little copper circles with a hole in the middle of it. So this will allow you to move the track. So for example, if you have a track on the top or a trace on the top, but you need to connect it to something on the bottom, you can use something like a via that will actually go through your board and connect it to the other side. That way, if you need some sort of trace that are crossing and you need those to cross, you can put a via, go underneath of it, come back out on the other side, and then it's okay. And we're going to go over a little bit more into like precautions you might need to take for that. But generally speaking, the vias, you don't need to worry about current unless you're going to be doing a lot of current. And in that case, you would just have multiple vias. So yeah, this is kind of what else. And in addition, you can also use vias to do something called via shielding. So if you have a very highly sensitive track with a high frequency signal going through it, you can actually calculate what that frequency is and then figure out the width you need between these vias to actually shield that wire from any interference, like electromagnetic interference that might actually hit that wire. So I'm just kind of mentioning that as something that you can use vias for as well. However, most of the time you're not going to be doing that unless you're working with like RF or really high frequency stuff. And then these are kind of your recommended general purpose via sizes. So for example, a large via size will have a pad, which is the little copper surrounding it, a pad size of 0.7 millimeters, and a drill hole of 0.3. So that's the actual hole there. So the pad size is the copper surrounding that hole, so that little like surrounding shiny bit, and the drill is the actual hole itself. And again, you can see the copper goes from one side all the way to the other. So there's copper inside that hole as well. So that way you can connect one side to the other. Next thing that I'm going to go over is actually really important. They call them polygons in PCB design, but essentially it's just any sort of plane that you can make out of copper. So, for example, I'll start off with this one down here. You can see that we have a trace coming through right here, and then there's a little gap in between that trace, and then a big red area on the outside. That red area on the outside is actually copper, just as like a giant plane underneath of it as well. And you're isolating those two traces with a little gap in between them. Copper pores are huge for any sort of tracing because it's hard to connect every single bit of your board. So, for example, if you have something like this trace right here, you'll notice there's no trace actually connected to it. It's just kind of floating right there. There's no track that goes to it. However, you probably can't see it from there, but if you look really closely, there's 4 little traces that go from the polygon or the copper pore on the bottom plane that connect to that via. So I'll kind of show a better example of that in a second here. but oftentimes your pour on the bottom will be your ground plane. The ground plane is the most common copper pour you'll be using, and we're going to be using that on the MPU 6050 that we're going to be doing. Pretty much any PCB you do, you need a ground plane underneath of it. And yeah, so they could also be used for heat sinks. So for example, you power people who are working with MOSFETs that switch a lot and actually gain a lot of heat. You can put copper around it that can kind of have a heat sink for that specific chip. So if you've seen heat sinks on computers, they're like big metal things on top of it, or heat sinks on chips where it's like little like fins, like aluminum fins, and it goes like and you go across it because there's a bunch of little fins. You can use copper pores to kind of do a similar thing to dissipate heat on really hot components. So things that are dealing with a lot of power, you can use to dissipate heat with the copper pore as well. Last thing I'm going to mention here is board stack. So I'm not going to go too much into detail into this, but there is an option. So for example, if you have your board, you have your traces on the top and your traces on the bottom, right? However, you can have things like 4-layer boards, 6-layer boards, 8-layer boards, all the way up to something crazy like 60-layer boards, which we'll never deal with. Most of the time, you're just going to be dealing with either 2-layer boards if it's a simple design, or 4-layer boards for something a little bit more complicated that has a lot more pins that you're going to be dealing with. I'm going to go back a little bit. Here is an example of a 4-layer board. So on the top, we have traces, those little wires of copper on the top connecting things. In between is a dielectric or insulator. So that's just like what the material of the actual like ruler in this case is made of. It's like fiberglass or something like that. But essentially, it's just a dielectric or insulator in between. Then the second layer right here is going to be right here, you can see. And in this case, it's a ground layer. So this is a ground pour using that polygon that I was talking about. So you can see it's not really traces like this, but rather just like a sheet of copper that's going to be on that plane. And for example, if there's going to be a via going through that plane, but you don't want to connect it to that big sheet of copper, there's little gaps in right there. So you won't be connecting that sheet of copper to any of the traces that go through there. So this would be your second layer. Oh, this might be a 6 actually. Yeah, it is. This middle layer, it might be a signal trace as well, signal plane as well, because you can see just like two small little traces instead of like a big plane. And then this fourth layer right here is another signal plane or signal layer. And then the fifth right here is a power plane. So that whole kind of big pad of copper right there is connected to power or VCC. And then again, on the bottom, we have another signal layer. So just to give you guys an example of kind of what a copper pour might look like on a PCB, I have the PCBs that we're going to be using for our soldering workshop coming up here soon. I put them on the table. These are not to keep, by the way. This is just for reference. So if you grab one of these, you can flip it to the back side where that Long Beach logo isn't happening. And you can see that there's a big kind of like different colored green surrounding the edge. And then you can see traces in there that isolate itself from that different type of green that you see there. So the big one that's around the edges, that's going to be our pour. So that's just a big copper pour around the edges like that. And then if we want something to go through that pour, we have those lines that go through there. So that way we can have a ground plane underneath that can connect things like you can see some of them have 4 little like edges going to the vias or holes that you see on this. So you could see like in the top right, I believe, it says J1. You see J1 on that board? It's on the other side where you can see the things. So you see J1. If you flip that around and look at the back where the holes are at, the circular hole has 4 little connections to that plane. So that hole is connected to our ground plane or that big copper pour underneath. We don't need to route an entire trace there. We could just simply connect it to that big copper pour underneath of it. There it is. In addition to that, if you're curious about vias, you can kind of look at the holes inside of there. These are also considered vias. In this case, we're going to be actually putting components through them. But you can see if you turn it sideways, the metal goes all the way through. It's not just on the top or the bottom, but the via actually connects the metal all the way through. So the next thing I'm going to kind of go over is clearance and rules. And this is kind of a boring one, but it's really, really important. When you're designing your PCB, you want to make sure that you can actually manufacture it. For example, if you want to make a hole that's like the size of the tip of a needle, the manufacturer can't make a hole that small. Or if you have a trace that is way too skinny, the manufacturer might not be able to actually make that trace. In that case, it'll throw an error. So for example, if you have an error happen, you'll see these green little circles, or it'll turn traces or things green in your software. In that case, then you need to go into your rules and the PCB rules and violations panel. If you remember in the bottom right panel, the bottom right of Altium, there's a thing that says panels. And in there, that's where you find your properties, your all these other information. In that same thing, there's a rules and violations panel that you can click there and change your rules and violations. The rules and violations depends what company is making your PCB. So for example, JLC PCB is the main one that we use, and they post, there's a big link that I posted here. So this is their capabilities of what they can actually produce. So you can go to that link and then see what they can actually produce, then go into your PCB rules and violations tab and actually fill out things like the 0.3 millimeter minimum hole diameter. So you can go in there and set those. So it'll let you know if there's an error or something happening, or if your manufacturer will be able to make that or not. I'm going to go a little bit more into detail on that in the computer once we do start. But that is just kind of just a quick thing to take note when you are making it. So placement. This is a really important one of where do you actually place your components. You have all these components flying around, but it's actually really, really important to put them in specific places. There's no true way to place every single component. There's just, you can hand someone 100 different PCB designers the same schematic, and they're going to all place them slightly differently. However, there's certain rules and diagrams that you should follow when you are placing components. So again, it's a great idea to divide those same blocks that you did into your schematic to actually be able to do those same kind of blocks on your PCB. For example, you don't want your power regulators to be on different parts, or the component that connects the capacitor to the power regulator over here and your power regulators right here. If you have a block of parts that are connected, you want to keep those parts together. So it's a good idea to, when you first start designing your PCB, create different blocks of your components, kind of put them roughly in the same area, and then kind of manage exactly their placement later on. Yeah, and then also there's a couple things that you want to make sure. So for example, power regulation would be one block, maybe the microcontroller another. Analog signals can be a one block, and maybe sensor suite. So things that have like all your sensors can be in one block as well. So first, you want to have your decoupling capacitors or bypass capacitors that we put into there. But if you remember from the data sheet, it showed us all the capacitors and where they need to go. And it's best practice to put those capacitors as close as you can to your actual chip, that you're still able to solder it and still have it manufactured. So try to have those capacitors as close as you can. So yeah. Another thing, so aesthetics. Again, this changes with everyone, but it is nice to see things that are kind of parallel, so you don't have resistors like one up here, one left, one right, but having them kind of neatly in a row makes it easy to actually find those components when you're ready to put them on the board. So you know, okay, that's 1, 2, 3, 4, so they're in a row. And so it's easier to find them on the board, and it just kind of looks better. But that's another key like thing to kind of think. But I think that'll come naturally when you're doing it. If something looks weird, change it. Okay, yeah. Once you do place it, you could do your design rule check, which is built into Altium. That is what I just mentioned before. So you set your design rules, and then you place your components, and then you can do a design rule check to make sure that those components aren't too close to one another. Or if two components, essentially make sure those components aren't too close to one another, hitting. Lastly, this is huge. I can't tell you how many PCBs I've done where I've messed something up. Every single PCB I've done, I've messed something up and I've had to do some way to fix it. The only thing that you can really do to avoid this is have someone review your schematic, have someone review your PCB, have someone really take the time to look through and figure out if it looks right. You know, there's something basic like on the last one, Leo looked over at my PCB and realized that when I copied a component over, it accidentally flipped it. So my transistor was pointing the wrong way. I was just copying and pasting things, so I didn't really take into a note what direction it was. And then Leo took one look at it and goes, that's backwards, you know? So it is incredibly important. I can't emphasize that enough. If you don't have someone to look over your PCB, come here and we'll happily look it over for a little bit. But it's incredibly important because no matter how smart you are, if you've been sitting down in front of a computer for like 4 hours doing a PCB, you're going to make one small mistake or two. So here's kind of an example of a board with good aesthetics and different block placement. So this one was actually done right here on campus by a previous student named Brandon Summers, and they did that for a rocket project. So this looks like a really cool board, right? It looks really pretty to look at. And if you kind of know what's happening, it's a little bit easier to follow. So he also did something really nice where he made a diagram where it shows the different blocks of what the components are. So here's the microcontroller, and he kind of labeled that nicely. You have your power input circuitry kind of all in one block. There's a buzzer right here. This is all your data information coming through right here. So all these things are kind of roughly put in the same block if they're associated. Then he has some more sensors. He's using an IMU. I believe he actually used the MPU 6050. I can't confirm that right now, but he used some sort of IMU very similar to the MPU 6050 on this exact board and placed it right here with the accelerometer. So this is a really good idea. So when you are designing any sort of bigger project with more blocks, being able to separate them and place them on your board efficiently. So it's easy to look at, it's easy to follow, and it looks better. So routing. This is very simple if you just look at the lines and follow them. However, in reality, there's a lot of things that you really need to take into account to reduce interference and things like that. So there's people with professional job for PCB designers just because they know how to properly route and do board stacks of high frequency signals and everything else like that, because it really is a complicated topic. However, I'm going to try to give you a very brief explanation as to why we do certain things. The first time I was designing a PCB, someone told me these rules and just said, hey, don't do this, don't do that. And I was like, okay. And I really had no idea as to why we were doing that. I'm going to try to give a brief explanation. If you don't completely understand it, that's fine. But I just want to give some explanation because I feel like I didn't get that when it was explained. So first thing is nets. If you remember in your schematic, you had your net labels. So those were labeling any things that are connected to another. So any sort of connection that is between two or more pads might be called a net. So for example, we had our power net. All of our power pins are connected to that same net. Yeah, so the next thing we have is power lines. As I mentioned before, you want to make sure that when you're doing your PCB, that the trace width can actually take the required power that's going through it. So if you stop and say, okay, well, my power input is going to be 6 amps, then you want to be able to look at that diagram and say, okay, I'm going to need a trace width of like 40 mils. And then in all honesty, I would just increase it more. I would have a bigger trace. You always want more wiggle room. So if for power lines, I would almost always recommend them to be a little bit bigger. And I'll show you kind of how to do that in a little bit. and same kind of goes with ground if you're going to have bigger ground lines. So communication lines. Communication lines in our case is the I²C. That is what the sensor is talking to our microcontroller with. This is the protocol or way that it speaks to one another so they can actually communicate. Your sensor is doing things, sensing its position and acceleration, but you want to be able to speak the same language to be able to go over to your microcontroller to take that information from the sensor. So the main thing with communication lines is you do not want to cross communication traces if you have a two-layer board like that. So, for example, if you have a trace like this going on top, right below it, you want a continuous ground plane. So you don't want something that interacts with that ground plane and makes a line in it. You can see on here, you can see examples of breaks in the ground plane underneath of it. So that would be an example of a trace directly underneath of it breaking the plane. So if a trace is above going like this, and it's a communication line, you want to have a continuous ground plane underneath of it, or take measures to mitigate that by maybe moving it to the other side of the board. In our specific case, we're using I²C, which is a 400 kilohertz communication frequency. It won't be that big of a deal. In all honesty, I've crossed traces on an I²C chip on a PCB in the past, and I had no effects. However, it's bad practice. Anytime you're doing a communication line, you want to try to mitigate any sort of EMI or electrical interference with other components, and crossing those components can do that. So, signal integrity. Signal integrity is kind of self-explanatory, but essentially having good signal integrity means that the signal that you're sending out of your sensor can actually be read by your microcontroller. So things like electromagnetic interference or maybe just any sort of noise that appears on a trace might ruin your signal integrity, and so your microcontroller might not be able to read it. This is also why we want to have a continuous ground plane underneath of it. It just improves our signal integrity. So lastly, EMI. EMI is electromagnetic interference, and that is just going to be any sort of, in your 360 class, you might have learned that any sort of alternating current or any sort of change in current can make a magnetic field. So I know a lot of you might not have taken that class yet, and that's completely fine because we have some diagrams to show you there. And I just want to note that I'm doing the explanations as to why we're not doing things. But really, you just need to know not to cross those communication lines. So if you're not following completely when I show the diagrams after this, that's completely fine. But again, EMI is electromagnetic interference, and any trace that creates some high frequency or frequency at all, it can become a bigger problem. So here's an example of a trace. So we might have a trace on top of the board, and some sort of signal with a frequency is going through that trace. That frequency will create a magnetic field on the trace, which you might see go like this, right? If you ever have two magnets, it's the same exact thing. They're both magnets and stuff like that. So you might have seen a very similar diagram to magnets before like this, and you'll know that as your magnets get closer, the connection between those two gets stronger. The same idea is kind of happening here. You want to have a ground plane as close as possible to a high frequency signal. Again, we're not dealing with too high frequency, but I just want to give you explanation as why we're doing this. So this is kind of going to be an example going over that high frequency and how it can do things that you might not expect to happen. So in this case, we have some signal coming in, right? And it's going to go through this wire right here. So this is a coaxial cable, but in the middle of it is going to be one wire, and then the surrounding outside of the wire is another connection. So it's essentially a 2-pin connector. You have one going through, and the second pin is just connected to a circle on the outside. So you can imagine the signal goes through here, goes all the way through this loop, comes to here, and then goes through some load. It doesn't matter what it is, but let's say we just have a resistor right here, right? Now it gets to this point and has two ways to go. It can decide to go all the way back here to our ground to reach the other side of it, or it can go through this much shorter wire that is just connecting these two. In this case, I'm going to say that this wire goes out like 50 meters. So this wire is going really, really far away. And as the wire length increases, so does the resistance on that wire. So you might say that electricity always takes the path of less resistance. So for something like that is really far, a wire that's going 50 meters might have a resistance of like 3 ohms or something like that. However, a wire that's only going like 30 centimeters might have a resistance of 0.01 ohms. So the electricity would want to take the path of least resistance, the side that has the least amount of resistance. So you might say, okay, most of the current will flow through this, all the way back here, through our load, and then straight through this wire, and then back to the ground. However, this starts to change as frequency increases. So we noticed before, as the magnetic field increases, that it's going to want to kind of attract or kind of go to the ground closest to that trace. So here's a graph showing the amount of current going through this wire as frequency increases. In a completely DC signal, one that is not changing in frequency, we don't have much of a magnetic field, right? Because magnetic fields start to appear once current starts stopping, going, or changing in any sort of way. So in that case, there's not much of a magnetic field. So 100% of the current that is coming out of here is flowing through this small little strap right here, this wire, and then going to ground. However, as we increase frequency, less and less current starts to go through that strap or wire. So it shows here that at 0 frequency, pretty much 100% of that current that is coming through the system goes through the wire. But as soon as we get to 100 kilohertz, almost none of it is going through that wire, and would much rather go the path of 50 meters all the way back to ground because it wants to couple to the closest ground. And coupling is just any sort of like opposite forces. So a magnet has a kind of opposite forces going to one another. And so in this case, the coupling is happening between this force, and they're equal and opposite because they're not moving. So as our frequency increases, by the time we get to 1 megahertz, virtually no current is going through this small strap. So you can take the same idea and apply it to something like this, where there's a positive and negative, and our ground separates between these three. So we have kind of a current divider. If you heard in your classes before, you have kind of voltage division where they're in series. And in this case, it's a current divider where everything is parallel. So the signal comes here and then it divides equally between these three if they have similar resistances. However, again, as our frequency increases, more and more current will not be divided equally between those three, but will instead be going through this one. Again, the reason is because now instead of the path of least resistance, it's the path of least impedance, which those two are they're very closely related, except impedance increases, impedance includes the frequency domain of any components. So capacitors, if you might have learned, they have a derivative if you're going to be solving for the voltage across them, or inductors have an integral, and derivatives and integrals are in the time domain, right? So as the time increases, that derivative or integral will change. So impedance kind of includes those time or frequency values into the resistance. So the path of least impedance starts to become the wire closest to the signal trace. How does that apply to PCBs? This is an example of a PCB where we just have one single trace at the top. So one of these traces that you see here is just going through the top. And then there's the kind of dielectric or the board in between. And then you have the bottom trace, which in this case is a big copper core. So this is just a big copper plane beneath right here. Now, these little white cutouts are cutouts into the copper plane. So for example, this one, there's no cutouts underneath the trace. This one, there's just one long cutout underneath the trace. And this one, there's a bunch of cutouts underneath the trace. And I kind of want you to stop here for a second, and just kind of think in your head, which one of these, rank which one will have the best performance in terms of EMI. So I just want you to say, okay, just choose 1, 2, 3, 4, or whatever that would have the best performance in terms of EMI.
Three.
So you pretty much are correct. So here is the graph of those. 1 and 3 are virtually the same. This is because there's an uninterrupted ground right underneath the signal. You can see right underneath the signal, it can couple to ground really, really close. It's just that. So most of our signal will be coupling to the ground directly beneath it. So 1 and 3 are pretty much the same. There's very little difference between the EMI signature of that signal. However, where it starts to become unintuitive is you might say, okay, well, there's a bunch of cutouts underneath case 4. So case 4 has a bunch of cutouts underneath of it. Therefore, there's the most like kind of unexposed, or the most copper underneath of it is missing. So there's a bunch of those missing traces. However, if we see here, case 4 is just slightly above this. And this is because the EMI, or the magnetic fields, don't need to travel all that far to get to couple to the closest point. So for a point right here to couple to the closest thing, it's right there. It's not too far. And as you get closer, the EMI signature, the magnetic field kind of coming off of that, whoops, wrong one, will not be that big because it can immediately couple to the ground plane underneath of it. However, case 2, you can see here, has way worse signal up here. It's way worse than the others. This is because this point right here needs to travel really, really far to try to couple to any ground planes right there. And so we have a way worse signal integrity, or EMI signature, or the magnetic field kind of coming off of that trace. And this magnetic field coming off that trace might start interacting with traces nearby it, or it might start actually losing some signal integrity. So this is why for communication traces, or anything that has any sort of frequency that is higher than 400,000 or 500,000, you want to make sure that you can have an uninterrupted ground plane underneath of it. And you'll kind of understand this a little bit better when we start doing it in Altium, which let me look at the time here and see how much time we have to get into that. But I just wanted to give you an example, but if you didn't follow any of that, all you got to know is that our I2C lines, or our communication lines, you want an uninterrupted ground plane underneath of it when we do design it. So I'll go ahead and show you how to do that now. What's up,